Swayam Prabha. Digital India. Educated India.
What I will do is I will just talk about the inner product that we spoke about. So, a few things were remaining which I want to mention, and then we will start and introduce concepts like linear independence and dimension. Okay. So, this inner product of u comma v we defined as vi through n, where each vector has n coordinates. Okay. So, basically what I am saying is, yeah, u is of the form u1, u2, u3, un, and v is of the form v1, v2, v3, vn. Okay. So, subscripts that I am using denote the coordinate, the first coordinate, second coordinate, third coordinate, or first element, second element, third element. We had to introduce this complex conjugate to make sure that we cover vectors which can also have complex elements. Okay. And we saw an example that if your vectors have complex parts, then the inner product of u with u can possibly be negative. Okay. So, we are violating that axiom, and so we wanted to generalize the definition of inner product. And again, although your vectors are real, but somewhere in the process of calculations you may get some vectors that are imaginary, and so we have just taken that into account in doing this definition. The important point is, if an inner product is defined, you can use that definition to define norm, the length, and if the length is defined, you can use that to define metric. Okay. So, that is the hierarchy. So, inner product can be used to define the norm or length, and then the norm can be used to define the metric. Basically what this means is, d of u comma v is the same as norm of u minus v, which is the inner product of u minus v to the power half. Okay. You can verify this. So, because in the definition of the metric and the norm, we have that square root for the Euclidean definition. Okay. But in the inner product I do not have a square root. That is the reason, after finding the inner product I have to put a square root, only then this will be equal. Okay. Now, two vectors are orthogonal or perpendicular, okay, if the inner product of u and v is 0, because remember the dot product is what we have generalized for the inner product, and it represents the angle, the cosine of the angle, okay, cos 90 is 0. So, basically if I say two vectors are orthogonal, I mean the inner product is 0 and two vectors are orthonormal u and v, these two vectors are u and v, okay, implies inner product of u and v is 0 and the norm of u equals norm of v equals 1. So, basically I have normalized it, means I have made the length equal to 1. I mean, you know how to do that, you just have to divide it by the length, then the length of the vector becomes 1, okay. So, if I say orthogonal, only this, if I say orthonormal, perpendicular and the length is 1. Now, and this again what we will see, we can have a set of vectors u1, u2, u3, un, okay. If I say that this set is orthogonal, that means every vector is orthogonal to every other vector, okay. If this is orthogonal, then inner product of ui with uj equals 0 for I not equal to j and is not equal to 0 for I equal to j, okay. You will see some of these things later on. So, I mean and I want to again emphasize that I am putting superscript to tell you that these are different vectors. Subscript is for the coordinate, superscript is for the vector. So, u superscript 1 is first vector, u superscript 2 is second vector, u subscript 1 is first coordinate, okay. So, I can have a set of vectors, and if I say this set is orthogonal, I mean u1 is perpendicular to everything else, it can't be perpendicular to itself. So, if I is equal to j, it is not 0, but if I is not equal to j, it is 0, okay. Similarly, u2 will be perpendicular to everything else, u3 will be perpendicular to everything else. Similarly, I mean the set of vectors ui, okay, is orthonormal if inner product of ui comma uj equals 0 for I not equal to j and inner product of ui with ui is not equal to 0, but because I have made it normal, this inner product will be 1, okay. This will be equal to 1 because there is the inner product, if I make it normal, the lengths become 1. So, basically if it is an orthonormal set, I have this property delta ij, which is the Kronecker delta, okay. So, this inner product of ui with uj will be equal to delta ij if you have an orthonormal set, okay. So, there is an advantage in dealing with orthonormal or orthogonal sets, which we will see later on, and that is the reason it is good to work with orthogonal sets. I want to introduce this concept of dependence and dimension. Okay. So, what are these concepts? We will see. Supposing I have two vectors u1 and u2 are two vectors, and let us say c1 and c2 are two scalars. So, like I said, no, the vector space will have field which has scalars and it will have vectors which are in the vector space. So, I have both of this, okay. And so, these are two different vectors and these are scalars. I can look at this sum, okay. If I can find, and let us say u1 and u2 are not 0, okay. u1 and u2 are not equal to 0. Now, if the only way in which this equation, this can be satisfied is if C1 equal to C2 equal to 0, then I will call it a independent set of vectors, okay. If this can be satisfied only by C1 equal to C2 equal to 0, then u1 and u2 are independent, okay. But if there can be a non-zero C1 and C2, see C1 equal to C2 equal to 0 will always satisfy, because we put 0 here, multiply this 0, multiply this will get 0. So, C1 equal to C2 equal to 0 will always satisfy, but the question is, can there be a non-zero C1 C2, okay. Can we have a non-zero C1 C2 which satisfies this? And if you can have a non-zero C1 C2, if we can have C1 C2 non-zero, then I can rewrite the equation as u1 equals minus C2 by C1 u2. Again, C2 and C1 are scalars, they are real numbers. So, C2 by C1 is also a real number. What this means is u1 is a scalar multiple of u2, or the other way, because C1 and C2 are non-zero, okay. So, basically if you have two vectors, if I am saying that they are dependent, that means that if they are dependent, that means C1 and C2 are non-zero, okay. Then u1 u2 are dependent, okay. So, what I have done is just illustrated this idea by taking two vectors. You can generalize it to R vectors, okay, any set of vectors. So, basically we want to extend this now. So, we generalize this to R vectors, that is u1, u2, etc. up to ur, okay, whatever I have said. So, a linear relation of these R vectors is given by sigma Ci ui equals 0 for I equals 1 through R, okay. So, I did for 2, now I am doing for R. So, basically what I am saying is you have C1 U1 plus C2 U2 plus C3 U3 CR UR. This is a linear relationship. Okay. Now, if all the CI's are 0, if all the CI's are 0, then this relationship will be trivially satisfied. It will always be satisfied. Okay. So, this is a trivial relation, and if at least one CI is not equal to 0, this relationship is non-trivial. Okay. So, if we have only the trivial relationship, which means only way that equations can be satisfied is if all the CI's are 0, all the constants are 0. Okay. That means all the CI's are 0, then the set is independent. So, I have an independent set if for that I need to do this sum of ui ci ui and see if I can get a non-zero solution. If I cannot get a non-zero solution, if I can get only ci equal to 0 as a solution for all the i's, okay, then I say this depend, is it correct? Yeah. And if at least one CI is non-zero and we can satisfy the linear relation, then set is dependent. Okay. There can be more than one, but let us take the simplest case 1. Now, even if it is more than 1 are non-zero, then it is also dependent. Okay. So, now just to keep things simple, let us say the first one is non-zero. Let us say C1 is not equal to 0. The first, everything else, then maybe others are also, at least C1 is not equal to 0, then I can write U1 as minus sigma Ci ui, okay, divided by C1, I going from 2 to R. So, what have I done? I have just taken the C1 U1 outside and then all the others I am combining. So, that is the reason I can do the summation from 2 to R and I am getting this. So, if I say dependent, what do I mean? I mean one of the vectors is a linear combination of all the other vectors. Okay. So, this implies one vector is a, at least one vector is a linear combination of all other vectors. Okay. So, that is the meaning of being this thing. So, I have my linear relation Ci ui equal to 0, I equals 1 through r, okay. And what exactly does this mean? This means C1 multiplied by the first vector superscript is 1, the first coordinate subscript is 1, 1 subscript 2, u1 subscript 3 up till u1 subscript n. So, all I have done is expanded my first vector u superscript 1 in terms of the coordinates, okay. Similarly, you have to do for the others, because second vector superscript is 1, and what is the last one? CR. Equals 0. Now, basically what is given to you, what is given to me is the set of vectors, the u superscript i's are given, okay, and what I have to find are the ci's. Is it possible to get a non-zero value, okay. So, ui's are given and the ci's have to be found out. Known ci's are to be found out. So, if you look at this and you can write this equation, you know, this is basically also going to be a 0 vector here. So, this is going to be an equation of the form C1 U11 plus C2 U21 plus CR UR1 equal to 0. That is the first. What have I done? I am just taking the first coordinate, okay. The first coordinate is taken and I am summing over the different vectors. So, how many such equations will I have? I will have capital N equations, okay. We will have capital N equations for each coordinate. And what are the unknowns? The number of unknowns is r, okay. So, basically what when it comes to trying to find out the solutions for Ci, I will have to solve a system of n equations in r unknowns, okay. That is what we are trying to do when you are trying to find dependence, okay. So, to find the Ci's, we have n equations in R unknowns, okay. So, let us consider the case where R is greater than n, that is the number of unknowns is more, number of equations is less. Then what can I do? I mean, n is the number of coordinates, okay, and r is the number of vectors. Then we can set whatever the extra things are, r minus n of the Ci's to be non-zero and find the other Ci's from 1 through n, okay. So, what we can do is we can have more unknowns. I can definitely put some non-zero value for those unknowns, the extra unknowns, extra variables, and then I will have a system of equations which I can solve for the others. So, what I am trying to tell you is that if R is greater than n, I will always have a non-zero Ci possible, and therefore, if R is greater than n, I will always have a dependent set, because now I have a non-zero Ci. Okay. So, hence here some of the Ci's are non-zero, and we have a dependent set. But if R is less than n, I cannot tell, less or equal to n, I cannot tell directly, it is not immediately obvious. So, if R is less than or equal to n, and we have to find if the relationship is trivial or non-trivial, and then decide. Okay. Now, this is as far as the concept of dependence is concerned. I want to introduce the other concept of dimension also. Okay. And so, I mean, we possibly have used the word dimension in a very loose manner earlier. For example, when you had vectors which have n coordinates, we said that belongs to Rn and the dimension of Rn is n. Okay. So, if we have a space, say Rn, what is Rn? Rn is a space, all the vectors which have n coordinates. Okay. These are vectors with n, I put small n, so I will put small n here, n coordinates. And we said the dimension of Rn is n. Okay. But I want to make it a bit more formal. I do not want to just say it is n dimensional space. I want to make it give you a more formal definition of dimension, and which can be for any general space. Then you will see certain extra things can come out. So, the dimension of a vector space is the maximum number of independent vectors, linearly independent vectors that you can have in that space. Okay. This is the formal definition. The dimension of a vector space is the maximum number of linearly independent vectors okay. So, I want to now formally prove to you that the dimension of Rn is n using this is the definition, and now I want to establish that the dimension of Rn is n. Okay. I mean, you were thinking, okay, Rn n coordinates, n dimensions, 2 coordinates, 2 dimensions, 3 coordinates, 3 dimensions. So, now I want to prove that the dimension of Rn equals n. So, clearly, if we take n plus 1 vectors in Rn, this is going to be a dependent set or an independent set. This is like what we had earlier as R vectors, okay, in n dimensions. So, this is like R, this is similar to the R, whatever that means, okay. And if R is greater than n, we saw that it is dependent. So, basically n plus 1 vectors in Rn is going to be dependent, because I can put one of them non-zero, number of unknowns is more, I can put that non-zero, solve for the others, okay. This is a dependent set, yeah, write the definition here. This is a dependent set. So, if I can prove that I can have n independent vectors in Rn, then that has to be the dimension, because that is the maximum. N plus 1 I know is dependent. So, basically my job is to prove that. So, we have to prove that we can have n independent vectors, then this is the maximum number possible okay, and therefore dimension equals n. So, what I want to do is show that consider n vectors ei, okay. What is ei? E1 is 1 0 0 0 etc. What is E2? 0 1 0 0 0. E3 is 0 0 1. Basically I am saying Ej has only the jth coordinate equal to 1, everything else is 0, okay. That is how I am defining my E1, E2, E3. So, E1 has only the first coordinate as 1, E2 has only the second coordinate as 1, everything else is 0, okay. So, I have a bunch of n vectors now, and if I can prove that this set of n vectors is independent, that is that if I do sigma Ci Ei, this will have only Ci equal to 0 as the solution, then that is the maximum set possible, and therefore the dimension is n, okay. That is the argument, okay. So, if we can show that Ci equal to 0 for sigma Ci Ei, I equals 1 through n is the only solution, then we have n independent vectors, okay. So, if I want to show I have n independent vectors, what I have done is I have just taken n of these, I mean I have just chosen these vectors which is easy for you to visualize. So, now if I look at sigma Ci Ei, okay, what is this? The C1 multiplied by 1 0 0, everything else is 0, okay, plus C2 0 1, everything else is 0, plus etc. CR C, what did I say, n, everything else 0 except the last one is 1 equal to 0, okay. So, what is this? This is basically C1 C2 Cn is equal to 0. So, the only solution possible is all the Ci's have to be 0, only then that vector, this vector will be equal to the 0 vector. Okay. Here only Ci equal to 0 for all I is possible. So, you can have, so what we have shown is in Rn I can have n independent vectors. N plus 1 I told you is already dependent, because number of unknowns is more than number of equations. You can set something to be non-zero and you can solve for the others. Okay. So, n plus 1 is dependent, n is independent, therefore, n has to be the maximum number of independent vectors, and therefore, the dimension of Rn is n. Okay. So, n plus 1 vectors are dependent, n vectors are independent, and this is the maximum number. Therefore, the dimension of Rn equals n. So, this is how you would formally go about showing that the dimension is n. Okay. I mean, you already knew it, but I am just trying to establish it, but this becomes important because there is this concept called subspace, which I want to introduce now. And I find most of the time people have difficulty in understanding this concept of subspace. So, consider, okay, a generating set, okay, a generating set of a vector space, no, generating set of a vector space is, let us say, ui. I mean have u1, u2, u3, whatever. I have some vectors. Okay. So, ui means I just put this curly bracket, so it's more than 1. This means every vector in the space, and let me call that space V, can be written as a linear combination or a scalar multiple of the vectors in the generating set. Okay. So, basically a generating set is the set of vectors which will generate all the vectors in V. How do I generate all the vectors? By adding 2 vectors, multiplying by some scalar, etc. When I multiply by scalar, I get a new vector. When I add 2 vectors, I get another vector. So, all these vectors are my vector space V, and the vectors which I am using to generate, that I am calling my generating set. Okay. So, now again try to be more precise to make the point clear. Consider (1, 0, 0) and 0, 1, 0. Okay. I am taking these 2 vectors, and I am going to take scalar multiples of these vectors and vector sums, again multiply by 2, multiply by 3, then add, just multiply by 2 and things like that. Okay. I am going to take vector additions and scalar multiples of these vectors if what is the space generated by these two vectors. What is the dimension of the space? These vectors all have 3 elements. Is the dimension, so I am looking at the scalar multiples and the vector additions of these vectors. They will all have 3 elements, but will they belong to R3? They will not belong to R3, okay, because the maximum number of independent vectors is only 2. So, this is basically going to generate these two will generate vectors with the x3 component, whatever the component, x3 component equal to 0. I cannot get a non-zero x3 component because this also has 0, this also has 0, okay. So, I can get vectors only in the plane of x1, x2, okay. So, basically what I am saying, I have x1, x2, x3. If I take those two vectors and do scalar multiples and linear combinations, I will only get vectors in this plane. I cannot get vectors which have any component in the x3 direction, okay. I cannot get vectors projecting out of the board, okay. And but every vector has 3 coordinates, only thing is the third coordinate is 0, it will always be 0 in this particular example, just to explain to you, okay. So, what this means is, this is not belonging to R3. So, the space generated by these two vectors is not R3, but it is a subspace of R3. It is a 2-dimensional subspace of R3 because I have 2 independent vectors. So, these 2 vectors I mean 1 0 0 0 1 0 generate a 2-dimensional subspace of R3. Why R3? Because every vector has 3 elements. Why 2-dimensional? Because only 2 independent vectors are there. You do all these combinations, everything is coming from only 2 independent vectors. So, dimension is 2, so it is a subspace, as opposed to R2. R2 also has 2 dimensions, but there are 2 coordinates, okay. You have to understand the difference. So, R2, this is not the same as R2, which has dimension 2, okay. Why? What is the difference? Because in R2 I have only 2 coordinates, okay. R2 I will have only 1 0 3 4 whatever it is, I have only 3 coordinates, but I have only 2 coordinates here, but there I have 3 coordinates, okay. So, I mean just because you have, I give you 3 vectors, and ask you what is the dimension of the space generated by it, you have to find out how many independent vectors are there. If there are only 2 independent vectors or only 1 independent vector, then it will generate a 2-dimensional space or a 1-dimensional subspace, sorry, okay. So, I mean you have to do that. So, let us stop